Good morning. So I'm recording lectures for 3.5 and 3.6 because two of my favorite students, Sabika and Sana, this year asked me to do that because they're not on my website. I thought they were, but I guess nobody's missed them. So sometimes I wonder if recording this and putting all the extra effort is really worth it because nobody seems to want it. Anyway, so Sabika and Sana really, to me, demonstrate an attitude that I really expect from my students, and that's the attitude of perseverance, of doing the work even though it's difficult, asking questions and seeking help, because that's what learning is all about. Okay, learning is all about not necessarily knowing everything at the first time. Okay, you've got to explore, you've got to ask questions, and you've got to persevere. Okay, so 3.5 is about limits at infinity, and what I'm talking about right now, what I'm showing you there is literally slides that I have for my pre-calc students, okay? And in pre-calc early on, we don't talk about limits at infinity. We do that later, but we do talk about horizontal asymptotes, which is also the end behavior. So quickly, let me explain the difference between horizontal asymptotes and limits at infinity. So supposing you have a function that looks like this. I'll change the graph in color. So let's say this is 2. I've got an asymptote like that, and here's my actual graph. Okay, say it looks like this. Okay, and this is the graph of fx. So as you can see, the graph is approaching the line y equals 2. So y is equal to 2 is an asymptote. Okay. However, if I say what is the limit as x goes to infinity of f of x, then the answer is 2. Because remember, a limit is a unique number that a function approaches as x approaches some quantity. Okay. So that's what is the difference between asymptotes and limits. So right here, this one here and this one here are two rational functions, okay? So if you remember from pre-calc and or chapter 1 in calc, rational functions are just a polynomial over a polynomial, okay? So there are 3 rules for finding the end behavior of rational functions, okay? So again, remember, end behavior, you can talk in terms of asymptotes, or you can talk in terms of limits. So the 3 conditions are A, B, and C. I know you can't see C clearly right now, but I'll just kind of go slow down, so that if you want, you can capture A and B. So if the degree of the numerator is less than the degree of the denominator, the x-axis is the asymptote. B, if the degree of the numerator is equal to degree of denominator, the line y equals the ratio of the leading coefficient of the numerator over the leading coefficient of the denominator is an asymptote. And if the degree of the numerator is greater than the degree of denominator, there is no horizontal asymptote. Okay, so those are 3 conditions for, remember, this is only for rational functions. In other words, a function where you get a polynomial over a polynomial. Okay, so here are 3 examples, and all 3 examples will be pertaining to the 3 rules that we just talked about. Okay, so if you take a look at example 1, then the degree of the numerator, okay, the degree of the numerator, that's this guy here, okay, its degree is 1. The degree of the denominator is 2, okay. And therefore, from the first rule, the limit is going to be equal to 0. For example 2, it's the second rule where the degree of the numerator is equal to the degree of the denominator. So that's the 2 degrees. Then the limit is a ratio of the leading coefficient. So the leading coefficient here is 2. The leading coefficient here, it's not there, but we all know it's 1. So then the answer is equal to 2. And the third example illustrates the third rule, rule number C, which says that the degree of the numerator, okay, is more than the degree of the denominator, then there is no limit. Okay, there is no limit. Okay, so that's 3 rational function examples. Two different examples, okay? These examples, there are no rules, but they can be done in a very different way. And let me explain how that's done, okay? So for example, for the first problem, okay, so let's call this number 1 and number 2, okay? You want to examine the limit of 3x minus 2 over square root of 2x squared plus 1 as x approaches infinity. So as x approaches infinity, you can say that this quantity here really doesn't contribute much to 3x because x is becoming a huge number, okay? So minus 2 really doesn't contribute anything. You can do a similar sort of analysis at the bottom. You can say that plus 1 doesn't contribute anything to 2x squared when x is becoming large. So then this limit is equal to limit as x goes to infinity of 3x over x root 2, which now cancels the x's, and you get the answer is 3 root 2 over 2. Okay. And you can verify this using your graphing calculator. So if I were to bring my calculator up and put in the equation in there, I get 3x minus 2 divided by square root of 2x squared plus 1. And if I graph that, I guess I need to change the window. I'm just going to go make it standard, okay? So actually zoom standard. So it's quite evident that there are asymptotes. So if you look at the asymptote as x approaches infinity, remember the asymptotes and limits are related, like I told you earlier. So the way you can do that is just bring the trace button out and move the trace over and look at what's happening to the y value, okay? Okay, so let's first of all go back and evaluate what 3 root 2 over 2 is, okay? So you get 3 root 2 divided by 2. Oops. (2.1213). Okay, so if I go graph that, bring my trace out again, it's approaching 2 point something. Let me just put a number in here and see. So this will be my x number is 50. I guess can't quite do that. Let me just change the window, okay? I'm going to change the window, x window, from 0 to, let's say, 100, assuming that you can graph that. And so if I bring trace up and put in, let's say, 99, my number is 2.11, so you can see it's approaching 2.12, okay? All right. Analyzing the second one is slightly tricky because of it going to minus infinity instead of plus infinity. So before I go there, let me just give you some conventions that have been established a long time ago, okay? You should know that square root of 4 means 2. It doesn't mean plus or minus 2, okay? In other words, a square root without a sign in front of it is always understood to be taken as a positive quantity, always taken to be as a positive quantity. So if I do the same kind of analysis that I did for the previous question, ignore that, then this becomes limit x goes to minus infinity of 3x over, now here's the trick, okay, this is x root 2. Well, if you take a look at me just writing like that, then there's an issue, because if I look at the quantity down here at the bottom, and you look at x going to negative infinity, meaning that all x values are negative, then the denominator is negative. But I just told you that with a pure square root, okay, with no sign in front of it, the answer should always be positive. So in order to fix that, I need to put a negative sign here, which then translates to negative 3 root 2 over 2. And our graphing calculator will show you that as well. So if I go back, change my window to be negative 100 to 100. Did that take? No. Right there, you can see that the limit is a negative number. So if I bring trace up and then take a look at negative 99, it should be negative 2.12, okay, 2.13, okay. All right, so it is approaching negative 3 root 2 over 2. Okay, some more examples. Okay, so these are trig examples. Okay, and if I look at the first one, okay, which is this one here, then you know that the sine graph does something like this. And you can see that as x approaches infinity, the graph is just going to oscillate, because since I don't know infinity, I don't know where this graph is going to, what it's going to do. It's not like it's settling down to any number, okay? It's just oscillating. So this one here is d and e. The limit does not exist. Okay. Try to analyze the second one. Okay, think a little bit differently. And there you know that this guy here, the numerator, can at most be plus 1 or minus 1. Okay? And then when you think about this number here being extremely large, you can think of it as saying that, hey, the top could be any number between plus 1 and minus 1, but the bottom is some humongous number. So you know that as the bottom goes to a humongous number, and if you divide and use that as in the denominator, then your results got to be 0, because let's say you've got 1 over 10 to the 10. Okay? That's going to be equal to 0. And if it's minus 1, 10 to the 10, then, well, there is no negative 0, so you get a 0. Okay? So the limit for the second one is a 0. Okay, a couple of more examples. Oh, no, I thought there was ones with rationalizing. Oh, I guess those must have been done in chapter 1. So rationalizing examples, I know you have to do them on your homework. So you might want to refer to some of the chapter 1 YouTubes and get it off there, okay?